Now I'm going to go through the history of synthetic aperture radar from the 1950s to the present, and just talk about how it was developed and the technologies used over 3 or 4 view graphs, so you can get a sense that it just didn't pop up yesterday. Because if you're someone fresh out of college or grad school, you don't remember World War II. You probably don't remember the Korean War, and you don't think too much of remembrance of even maybe the Vietnam War, where I was in grad school at the time. But anyway, for me, this is the time I got out of grad school, but well before that, in 1951, the SAR concept was invented by Carl Wiley at Goodyear. And here's a photo, the only photo I could find on the web, of Carl, who did that historic invention of the synthetic aperture concept. And by 1953, there were demonstrations of what I'll call, you'll learn later, unfocused SARs, and then at Willow Run Laboratory in Michigan, which became the Environmental Research Institute of Michigan, the first focused, another term I'll describe, better resolution, synthetic aperture radar was tested. And these radars took all the processing of all those pulses, and what they do is they have to use, well, they didn't have A to D converters. Let's start with the problem. So how do you do a lot of processing, which involves Fourier transforms, where you've got data coming out, amplitude as a function of time? What they did was they took photographs of the amplitude as a function of time data, and they put that on film. And that film was then offloaded off the plane after it did its reconnaissance. The early role of synthetic aperture radar until the digital revolution was always reconnaissance, because it couldn't do anything in real time. You have to take the load of film off and then process it optically using coherent holography-based laser technology to implement Fourier transforms. And that's what the first data came out. Now here is the first successful focused airborne synthetic aperture radar image, and it was taken of the Willow Run Airport, and that's near Ann Arbor, Michigan, in the vicinity, and it was in August 1957. We mark it here. Here we could see the airport, and that's courtesy of the University of Michigan. And out of this lab, the Environmental Research Institute, and that later became a nonprofit, Verizon, and then was acquired by General Dynamics, I believe. Then it was realized that doing these optical transforms was difficult in the polar format in which the data is collected. Here you can see you transmit out to a range, and then you sample it in range, and then take the Fourier transform, and then you're going to want to take another Fourier transform across the aperture. And the polar format processing, where we go and we interpolate the data into a matrix that has uniform spacing, really helps do the Fourier transforms, and that's a key development, and that happened in '78, but was still done optically. The Fourier transforms were done. Now, in 1978, this satellite was launched by NASA with JPL doing the bulk of the radar SAR development, I believe, and it's the first satellite with a SAR capability. And here you see where it was launched, and here's a CSAT image of waves in the ocean off of the southern coast near Yakutat, Alaska. And this is a CSAT image. Now, here's where we come in, and life gets very different. And I'd say it's about 79. A to D converters got to a point, and digital processors got to a point where they were very mature. We could get A to D converters that had really the kind of dynamic range and sample rate, and they were linear, to handle the kind of processing that is done with these SAR radars. And once you could do it digitally, at the same time, in the early 1970s, Oppenheim and Schaefer and others really developed the formalism of the field we know as digital signal processing. Before that, in the mid-70s, Ben Gold at Bell Labs and Ben Gold at Lincoln Lab wrote a book about that thick on digital signal processing, but it really didn't give the solid formalism to it that Alan Oppenheim and Ron Schaefer did in their classic book, Digital Signal Processing. And in 72, I believe it was, I took a one-week course in digital signal processing over the summer at MIT. And believe it or not, they taught that whole bloody book in 2 days. And then they taught a book that Gold and Rabina, Ben Gold and Larry Rabina wrote on filter design in the next 2 days. Man, that was drinking from a fire hose. So much of it went in one ear and out the other. I took the course slowly at Lincoln Laboratory a year later and did it. You know, it's trying to like eat all your food for a week in 1 hour. You just can't do it. But anyway, they passed out. That's memorable to me because they passed out galley proofs of both those two seminal first texts in both digital filter design and the digital formalism of Al Oppenheim and Ron Schaefer. Many other authors have since put out other books. And now that was something that wasn't taught as even in graduate school before that text came out, I don't think. It might have just been started to teach with lecture notes. But now undergraduates learn digital signal processing. So what we have is the dawn of the digital revolution, which really brought SAR into its own and got the algorithm people, the people that developed that intellectual property to do magnificence with high-speed computer and Moore's law. Once you had those A to Ds and the fast computers that kept faster with Moore's law, all kinds of things we were able to do. In the mid-1980s, on U-2s, they called them TR-2s at the time, there was a reconnaissance aircraft, and it had an ASAR-2, which was an airborne SAR, and that was in the mid-80s. And then Joint STARS, which we talked about in airborne radars in the context of ground moving target indicator. It has a SAR mode, and that came out in '88. And then later on, the Magellan probe, which was developed by NASA, but JPL did, I believe, was very, very heavily involved in the radar design, if not the lead. They sent a probe out to orbit Venus. Now, if you look up with a telescope, you will not see this picture. Venus is covered with noxious, poisonous gases that optics and IR can't see through. And so what you have to do is to send out good old microwaves. And a little below 3 gigahertz was the frequency used. And it sent out, the probe was sent out, and it orbited in a polar orbit, Venus. And Venus would just slowly rotate around, and the radar would point towards Venus and collect images. And it completely mapped Venus to 100-meter resolution, an entire planet whose ground had never been seen, the resolution to 100 meters. I'm going to show you later that doing tricks with this with multiple orbits allows the sensor to measure height of craters and things on Venus too. And this is a crummy image relative to the big ones I'm going to fill the screen with later. Now also in 97, remember this is in 89 that this went out. In 97, another fantastic probe, Cassini, went to Saturn, and it took SAR images of Titan the largest moon of Saturn, and we're going to see some of them later. It was one of those swing bys that did Jupiter and Saturn, but when it got to around Saturn, it oriented itself so it could point directly towards Titan, and that's way in the outer part of the solar system, and returned fantastic images of what that largest moon of Saturn is. So we're going to see great pictures of that. I love to put these the movies in so you can see the little guys going around. Okay, now also in this time range, 2000 plus, we've got a lot of work done by Sandia and earlier. Sandia has become one of the stars one of the few great stars in the development of remote sensing SAR technology, both for the military and for remote sensing. And here we see two very popular buildings. There's a SAR, I believe it's KU band, we'll see in a minute, that's on a twin otter. It's right down there. Oh yes, it is a KU band, and it's got 1 foot resolution, and it's flying up probably 10, 15, 20,000 feet. And here's an image, 1 foot resolution of the Capitol. Why they can't get things to work, I don't know. And here we have the Pentagon to 1 foot resolution. And these, you're going to see a lot better images of these, of other things that Sandia has done. And I also want to note here that in the military, people are making fire controls with phased array radars. Here for the F-35 aircraft, the latest fighter aircraft for the Air Force. It's a multi-service, excuse me. This is an Air Force photo. But the F-35 is multi-service. Here is with the nose off, you can see the Agile electronically scanned array, and it has a SAR mode. Not only does surveillance and tracking and whatever, but it has a synthetic aperture radar mode, so it can map the ground, find targets, do damage assessment, that sort of thing. So the most modern of our military equipment and the most modern of our remote sensing use synthetic aperture radar. And you're going to see a lot of examples of that. Now, in terms of SAR resolution, why, it's only getting better. And the thing to note here, here's the resolution in feet, and notice this is a logarithmic scale, and it's going over a factor of 1,000,000. Well, 10 to the 5th, almost 10 to the 6th, when I start up here. This is just when we're dealing with a real beam, just an ordinary beam, no synthetic aperture radar, unfocused or focused or what have you. And these are the names of some radars and how the resolution got better and better. And here's an airborne SAR in the 80s, and now we're up at levels where we can see down to the order of inches, 10 to the minus 1 feet. So that's pretty darn good. Okay. Now I want to show you a picture or two of, again, go back and show you some nice pictures of SARs with big images. This is a synthetic aperture radar that's an X-band. That's an R&D radar, in that we're not trying to pack it. This wasn't developed to be packaged on an operational aircraft. It's a X-band radar. It's an active electronically scanned array on the nose of a 707 right here. And inside the body of the ship, of the aircraft, are the receivers and A to D converters. And so the algorithmic people can play with the data before it's all made as small as possible. There's a 3.5 terabyte RAID recording device which can capture a huge number of hours of data, so that can be processed later on and to the best of our ability. And notice the inertial measurements unit, because you're going to see later you really need to know exactly where that antenna is, because we're going to be correcting pulse by pulse by pulse for the position of that antenna to correct the phase, so that we've got a perfectly spherical wave that we're processing through the signal processing. So we just do the receivers, A to Ds, and collect the data raw. Now here's just the 30 centimeters the Lincoln multi-mission ISR, that's Intelligence, Surveillance, and Reconnaissance Testbed, SAR. And this whole business here is 500 meters, half a kilometer by 830 kilometers. And this is to give you an idea how you can see, you can just see, here's a building, here an obvious road and an intersection. And you can see stopped at the intersection these white dots. And because it's an attribute of synthetic aperture radars that if an object, it assumes all objects are stationary. So if you have one moving, it blurs in the SAR image. And here we have a car that's pulling up behind these other cars that are presumably stopped at a stoplight. And these two haven't quite come to a stop. So we see a blurred image, another blurred image here and here. Over here, we have a building with a parking lot, and in the parking lot, we have another blurred image and another one of objects that are in the process of parking. And the same with this in a parking lot and here we see another road and buildings and parking lots. In the Sierra Vista, Arizona area, this image was taken in August of, as you can see, 2005, with just 30 centimeters, about a foot resolution-ish. Okay, now what are the missions and platforms that are used? And we're just going to spend the next 5 view graphs looking at the missions. And the missions, of course, the first one that I'm going to talk about is military. Why? Because it's on the view graph. It's military. They're both very important. And it's intelligence, surveillance, reconnaissance, and also treaty verification, because you can put these in satellites and verify arms control treaties with them. And remote sensing, I can show you, I don't know if I'll have it, but people do ice cap erosion measurement with Earth surveillance from satellites or from planes. I showed you the example of planetary characterization, just earth-shaking science measurement of the mapping of Venus. Monitor the ocean currents for El Nino and things. Many, many, many other roles. You'll see the journal on geophysics and remote sensing. The IEEE has a society in remote sensing. If you just Google remote sensing and SAR, you'll get thousands upon thousands of journal articles if you Google Scholar. And of course, these are on the following platforms, as we've seen: aircraft, satellites, and space probes. And so we'll look one at a time in a reasonable, orderly way at these different missions. First, let's look at synthetic aperture platforms for airborne systems. I already showed you the F-35 and the APG-81. This is a little bigger, easier for you to see. You've got the Lincoln Lab experimental testbed. There's a SAR in the Global Hawk unmanned air vehicle. Predator has a synthetic aperture radar in it along with other sensors. And joint stars, as we looked earlier at the history, have. So here's some of them we've already seen, and there are others too. And SAR platforms and satellites and space probes. I've shown you Magellan. Here's a little bigger image of Cassini. The European Space Agency has put up a remote sensing satellite, ESA-2, which I think if it isn't up, it's going to be up in months. ESA-1 has been up. They're in the business, and Germany is putting up a SAR called Lupe. And the Space Shuttle Imaging Radar has been up for a long time. When that shuttle mission transpired, it had a C and X-band array in it. It flew for a while, and then several times, I think, and then imaging the Earth to great detail at C and at X-band. And then later, they put a 60-foot boom with dual receivers out perpendicular out from the view graph so that they could measure, using this system, height above the ground. We're going to look and see that later, blown up pictures of that It has its own acronym for when they were in the height measure, when the shuttle imaging radar was in the height measuring mode. So you see that. Now we go into airborne platforms for remote sensing. And this is also to point out ARM's a heavy player. I'm not that sure. I'm actually not knowledgeable of what they're doing now after the different mergers. Sandia is a really big player, and I wanted to show a picture of their P-3 aircraft, which has a SAR here and here in these pods. And NASA has synthetic aperture radars that they use for remote sensing and other missions. And here's the de Havilland Twin Otter up close with Sandia's SAR. And they have other synthetic aperture radar systems. Okay, now that's the end of the of this section. And next we're going to look at, but not right now, we're going to take a break, synthetic aperture basics. And we're going to look at all these different things. This will probably break up into a couple. What I'll probably do is go over very carefully the algebra, remind myself. I can tell you I have not looked at these view graphs in 6 months. I developed them last January. Well, from January to June, I developed the actual view graphs. Did a lot of reading before that. And then things went down when I had some health issues. And this is, today is the first day I've really looked in detail at the SAR stuff. So, the first is easy to lecture on. This I want to review so that I don't forget crucial words and I have my words put together appropriately, and so I can be a good teacher. So now we'll take a break.